Hello. So today what we're going to be doing is I'm going to be taking up the mouse problem, and then we're just going to look at quiz 2. I'm going to take up the quiz from 2012. And so let's start. So you're given the following schematic below. So we don't need the schematic. We can actually erase it. We're told the mouse is initially 20 centimeters away from the camera, following a line of sight with the origin at the camera. The mouse then moves 40 centimeters and the camera rotates 35 degrees counterclockwise as it continues to follow the mouse. What is the distance from the mouse to the camera? Support your solution with a sketch. So let's start with a sketch first, so we can understand what's going on, and then we'll start solving. And you'll see that once we draw the sketch, it's actually quite simple. So today I'm drawing with the mouse, so sorry if it's messy. So let's start. So here's going to be our camera, and then this is going to be our mouse. So originally, these 2 points are 20 centimeters away. Then the mouse moves 40 centimeters away from the camera. The mouse then moves 40 centimeters. So it moves 40 centimeters. Let's say it moves right over here. And that's a perfect straight line. Let me adjust it. So there you go. It moves 40 centimeters. And the camera then rotates 35 degrees. So if initially the camera was staring right over here, the camera then rotates 35 degrees and starts staring over there. So that angle there would be 35. And then if we draw a line, what we see is we get a triangle, right? And so what do we know? We know that so if we call this triangle A, B, C, and we know AB is 20, that was the initial distance. We know the mouse moves 40 centimeters. We know that the rotation of the camera is 35 degrees. So now we just need to calculate AC because that's the distance between the camera and the mouse. Okay, what we're going to use here is we're just going to use sine law. That states that A over sine alpha equals to B over sine beta, which equals to C over sine gamma. I don't know how to draw gamma. I'm just going to say C. Perfect. So now let's use that. So what we're going to do first is we have our side. We have an angle. And what we're going to do is we're going to find this angle over here, angle C. So then we could find this angle, and finally we could find AC. So how are we going to find this angle over here, angle C? Well, again, sine law. So we're going to go 20 over sine of C equals to 40 over sine 35. Perfect. Now we're just going to isolate for C. So sine of C equals to 20 times sine 35 over 40. C equals to inverse of sine, arc sine or sine to the power of -1, 20 times sine 35 over 40. So this angle is equal to about 16 point something. I don't remember, but it's 16 point something. But when you actually enter it into your calculator later, for this angle, you want to have exact. Depending on the calculator, you can usually do that with just ANS. So now we're going to find angle B. And finding angle B, it's as simple as just going 180 minus angle A plus C. And so angle A is 35 and C is 16, just as we calculated, it's about 16. So the new angle we get, angle B, is going to be equal to 54.7. 54.7 or 128. Oh, I forgot. I think it was 128. Now that I think about it, it was 128 actually. So sorry for my mistake there. It's about 128. So then what we're going to do, now that we know angle B, we can now calculate this side, AC. That's just going to equal to, so it's going to be AC over sine of 128 equals to 40 over sine 35. And we're going to get AC is equal to 40 times sine of 128 divided by sine of 35. And that is about equal to 54.7. 0.7. And so it's going to be 54.7 centimeters away from the camera. And there you go. That's how you get that. Okay. Now what we're going to do is we're going to take up the quiz. And what I'm going to do is I'm going to be looking over here, looking at the question. There's an answer here below, so you can also look over that, but I'm just going to be taking it up. So let's start. Convert the following point from polar coordinates to Cartesian coordinates. And so the polar point that we get is 2 pi over 3. 2 pi over 3. So now the way you convert from polar to Cartesian is as follows. What we're going to do is x is equal to, this is our radius, so it's radius times cosine of theta, and y is equal to r times sine of theta. Now, the way you can remember this or understand why this is happening is if we look at our Cartesian plane, right? Right over here. So now, if we draw our line right over here, so let's say this was our polar coordinates. Go back to polar coordinates. So this would be theta, and this would be r. Now this over here, if we want to express it in Cartesian, we would need to have this as x, y. And that, if we think about it, x, y, this over here is equal to x, and then this over here is equal to y. And we can get those two just by using simple trigonometry, right? Because y, so what is it called? Cos of theta would be equal to y over r, and that's why r cos, I meant to say sine. I probably confused many people there. I'm sorry, that was a mistake. So y is equal to r sine theta. And then we would get x is equal to r cos theta. And that's what we get right over here. Perfect. So now we can just plug in our numbers and figure it out. So x equals to 2 times cosine of 2 pi over 3. And so 2 pi over 3 is 120 degrees. So 120 degrees lies in my second quadrant right over here, where cosine is negative. So we know it's going to be negative. And if we draw our triangle over here of 120 degrees, we notice that this is going to be 60 degrees, or pi over 3. So cosine of 60 is equal to 1/2. So it's actually going to equal to -1. It's 2 times -1/2. Next, we're going to get y, and y is equal to 2 times sine of 2 pi over 3. And sorry for the ugly handwriting. I'm just using a mouse here. 2 pi over 3. And again, this is our second quadrant, so we know our sine is going to be positive. Then we're going to go 2 times, and sine of 60 is root 3 over 2. So it's going to be 2 times root 3 over 2, which is then equal to root 3. And so then our coordinates in the Cartesian would be -1 root 3. And just as a quick reminder, because it might come up on the test tomorrow, I don't know, to go from Cartesian back to polar, you do it like this. So what you do is you say, first you want your radius, and radius, we just use the Pythagorean theorem to find it. And so r squared is equal to x squared plus y squared. Therefore, r is equal to square root of x squared plus y squared. And in our case, that would be r is equal to square root of -1 squared, which is 1, and root of 3 squared, which is 3, which would equal to root of 4, which would equal to 2, which matches up. And then to get our theta, or our angle, we're going to take the inverse tan. So theta is equal to a tan y over x. And this makes sense because if you just look at our triangle, we have tan of theta is equal to opposite over adjacent, which is y over x. And that's how we go there. So a tan of y over x. And that's how you can always remember that you put the y coordinate on top, and then it's y coordinate over x coordinate. And so then that would be root 3 over -1. And so of -√3, you can see that it's going to be right over here. And so a tan of, so what I was going to say is that you know that this is happening in the second quadrant. That's the better way to do it. So let's scratch that. So you know that this is happening in the second quadrant because you know that -1√3 is in the second quadrant. So then you take a tan or inverse of tan of √3 over 1. So you know that a tan of √3 is 60 degrees. And then because you know it's happening in our second quadrant, you can then deduce that it's going to be 120 degrees, which we're talking about. Okay, cool. Let's go on to the second question. The second question over here is about our distances. So plot the 2 points, 1, 1, and -2, -1 on the Cartesian coordinate system. Okay, great. I'll just move over right over here. So let's draw our Cartesian coordinate system. I'm sure that everybody can do this part. So 1, 1, 1, 1 would be right over here somewhere. And then -2, -1 would be like -2, -1 is somewhere over here. Just mark it -2, -1. And then this is 1, 1. Of course, you would be more precise if drawing on a test, but this is just about right. And then what we need to find is we need to find R2 distance and R1. And I'm just going to find Chebyshev's distance as well, just so you can do it if you need to on the test. So to find R1 distance, or L1, I don't remember the denotation exactly, but to find R1 distance, what you do is you take the absolute value of the delta x plus absolute value of the delta y. And what does that mean? That means that if we think about it, it's this distance over here. So you're going to add this length over here plus this length over here. So in our case, it is going to be equal to delta x is going to be 1 minus -2. That's going to be 3. And then 1 minus 1 is 2, so plus 2. That is going to equal to 5. R2 distance is this distance right over here. That is R2. So R2 is just, again, we use Pythagorean, so that's why it would be square root of delta x squared plus delta y squared. And so we would get square root of 3 squared plus 2 squared, which would be equal to square root of 13. And that is 13, guys. Perfect. And our 3 Chebyshev distances, you're just taking the max. So it's going to be max, the biggest one between the absolute value of delta x and the absolute value of delta y. And that would just be in our case, so delta x is 3, delta y is 2, and so that's why this would be equal to 3. Perfect. See, for now it doesn't seem too bad. Let's go on. So now what we're going to do is we're going to find the roots of -j27 to the 1/3, and then we have to express it in our rectangular form. So let's do it. So we're going to move over right over here. Perfect. And now let's do it. So we're going to take the -27j to the power of 1/3. And we need to find the roots of this imaginary number. So the way we're going to do that is we're first going to make it into its exponential form. Now, the way you make it into the exponential form is actually the exact same way you make it into your polar form in essence. And that's just like this. So first we need to find the modulus. So modulus z is equal to square root of your real part squared plus your imaginary part squared. In our case, we don't have a real part, so it would just be square root of, so this is r squared, so it's 0 plus 27 squared, not -27 because you have, what is it called? Because it's just squared, so that's why I don't care. And that's just going to end up being 27. So our modulus is going to be 27. Again, just to remind, exponential form is this form, so it's modulus z times e to the I theta. So then our modulus would be 27. So it's 27. And then we need to get our angle. And our angle is a tan imaginary part over real part. And you can think of it as the imaginary part is y and the real part is x. And in our case, that would be a tan of negative 27 over 0. This would give us negative infinity, I believe. And because we get, I'm just checking my answers here so I don't lie to anybody. So yeah, that should give us a negative infinity, which would then give us pi over 2, negative pi over 2. So our angle theta is equal to negative pi over 2. And I know Miss Cart really likes to draw, so I'll just draw it out here quickly as well. So again, if we look at our real and imaginary part, this is our reals, this is our imaginaries. And because we know we're on our imaginary plane, it actually makes sense that we're going to have negative pi over 2. My drawing was more to confirm that our theta is real, but it makes sense. I mean, so again, you would just go down over here, it'd be at negative 27, and it makes sense that the theta is pi over 2. Great. So now we have our modulus and our angle. So we're going to get 27 e to the I negative pi over 2 to the power of 1/3. And now we know we're going to have 3 roots because it's the power of 1 over 3. If you see the 3, it's 3 roots. And so now what I'm going to do is I'm going to rewrite this quickly. And I'm just going to say that e to the I negative pi theta, you can actually add plus 2 pi k. And the reason you can add that is because if we go back here, this is a 360-degree circle, right? And so if we have an angle over here and we add 2 pi to it, which is 360, so if we add 3 pi over here, let's go orange. So if we add 3 pi over here, 2 pi over here, this is going to be 360 degrees. And the reason it's 2k pi is because you can add you can make as many loops as you want. So k just represents, in essence, how many circles you're making. So if k is equal to 1, that means you're making 1 circle and you're ending up back here. If you're adding, if k equals 2, you're doing 2 circles and ending up back here. And so that's why when we go back to our exponential form right over here, we are going to rewrite it like this. So 27 times e to the I negative pi over 2 plus 2k pi. And that just indicates that you can, that angle, you can spin it 360 degrees. And all of this to the power of 1/3. Now what I'm going to do is I'm going to expand. So I'm just going to put 1/3 into here. So the third root of 27 is going to be 3. So it's 3e to the power of negative I pi over 6 plus 2k pi over 3. Perfect. And now we can start finding our roots. The way we're going to do that, we're going to start by setting k to 0. So that's going to be our first root. If k is equal to 0, then what happens? Then we get 3e to the negative I, to the negative I pi over 6, and 2k pi over 3 disappears because k is equal to 0, so it's going to be 2 times 0. 0 over 3 is just 0. That's our first root. And I know it's at rectangular form. I'm going to transfer all of them into rectangular form after I finish. So let's go k1. So k equals to 1. So now if k equals to 1, we're going to get 3 e to the negative I pi over 6 plus, and now if we put k equals 1, we're going to get 2 pi over 3. That is equal to 3 times negative 3 times e to the negative, I'm just rewriting that. Sorry, I lost my train of thought. Negative I pi over 6. And then we're just going to make 2 pi over 3 also have a denominator of 6, so we can add. It's going to be plus 4 pi over 6. And that is going to equal to 3 pi over 6. So 3e, 3 pi over 6, which is just going to equal to 3e to the 1/2 to the pi over 2. is what I meant to say. 3e I pi over 2. Okay, and then finally, we're going to find our third root, and that's at k equals 2. Equals 2. And at k equals 2, that's going to be 3e negative I pi over 6 plus, and if we substitute 2 into here, it's going to be plus 4 pi over 3. That's right, yeah, 4 pi over 3. That's going to equal to 3 e to the negative I pi over 6 plus 8 pi over 6, which is going to equal to 3 e to the I 7 pi over 6. And now I'm going to, so now what I'm going to do is I'm just going to transfer some of these over to rectangular form. And also because I don't know if we're going to have to draw them, I'll also quickly draw them. So I'll begin with the drawing because I think it's easier, and then we'll transfer over to rectangular form. So if we draw it, what we see is that we're going to have, our first root is going to have, firstly, a modulus of 3. So that means the radius over here is going to be 3. Let's draw a radius of 3. And let's make this line green. We like green. We're going to pretend it's Christmas. So over here, we have a green over here. And then negative pi over 6, so that's 180 over 6, which means that it has a degree of 30 degrees. So then we're going to rotate this quickly to make it resemble that it's 30 degrees, and it's 3, so somewhere over here. So theta over here would be 30. Then our second, so this would be our first imaginary number. It would be located somewhere right over here. Point, but you could imagine it like right over here, as with the line, but the actual point would be over here. Then what we could do is we can think of our other points. So then our next point would be pi over 2, so it would be at 90. So it would be right over here at 90. And then our third point would be at 7 pi over 6, so that is going to be 210. 210 should be somewhere right over here. I'll check that just for fun. So 7 times 7, I don't know what I'm checking. I know that 7 times 30 is 210. What I meant to say is that does look right, because this is going to be, this is somewhere about 270, so 210 should be somewhere over here. And I want to just point out one quick thing to you, which might be helpful to you during the test. If you see that it's 3, then basically what we're doing is we're dividing this 360 degree by 3. And so the difference between all of these is actually 120. So this is 120 degrees. This is 120 degrees. And this is 120 degrees. If you draw the lines, you can see it maybe a bit better. But that might be helpful because, for instance, if you have four roots, then you know that the difference between them will be 90 degrees. And then if you have 6 roots, each root will be 30 degrees away. And so if you do end up drawing it, if it looks like each one is about 30 degrees away from each other, it'll be a lot better. Perfect. So now let's make this into rectangular form. So the way you make it into rectangular form is you make it first, you transfer it over to polar form, which is 3, that's our modulus, times cosine of our theta, and our theta is negative pi over 6, negative pi over 6, and then plus I sine the negative pi over 6. And so then I'm going to simplify this. So negative 30 is located in our in our fourth quadrant. So cosine is positive here, so it's going to be positive, and then because it's a degree of 30, it's going to be root 3 over 2. So it's going to be 3 root 3 over 2. And then our sine is going to be negative again because we're in the fourth quadrant, so it's going to be minus. And then sine of 30 is a half. So it's going to be 3 over 2i, 3 over 2i. And the 3 I just got by multiplying it in right away. I kind of skipped a step there. Okay, and now, partially because I'm lazy, but I'm going to say I'm not lazy, and I just want you to do something or practice a bit more. If you want to, you can transfer over these into rectangular form. And again, you're just going to plug in the angle there and see, and then multiply the 3 in. Okay, perfect. let's move on then. And you can check afterwards if we got the same answers, and I think we did. Okay, so then here we have you're given the following routes, which are plotted on the diagram. An ag diagram is if you just take the ag diagram, it sounds very grandiose, but it really isn't. From what I understand, a grand diagram is just like this. So, and then this is real, this is imaginary. So it's basically Cartesian plane, but instead of X and Y, you have R and I, and it's called the Argand diagram. And now let's try to figure out how we do this. So the answer is given here, but let's try to figure out how we could do it if we don't know the answer. So you're given the following routes, which are plotted on the end. Our Argand diagram, so 1e pi over 4, 1e3 pi over 4, 1e5 pi over 4, and 1e7 pi over 4. So right away, what we notice is that there are 4 roots over here. And why do I say that? That means that what we are taking is going to be to the 1/4. And you'll see why this is really important. So this is, it's going to be taken, so we're taking some e, or some imaginary number to the 1/4, and that's why we're finding 4 roots. Now what we're going to do is we're going to look at our modulus. So our modulus right over here is 1, and our angle is pi over 4, and pi over 4 is 45, if I'm not mistaken. No, pi over 4, yeah, pi over 4 is 45. But what I meant to say is that because we're taking 1 over 4, that means beforehand, the 4th wasn't there. So what we're taking to the 1/4 power is before that. So in essence, what I'm trying to say is we're factoring out that over 4. So if you think of before we actually made this go in, it would be just e to the pi. 1 e to the pi 1/4. And that's how when you multiply it in, you get pi over 4. And that means that beforehand we had e to the pi and 1. And so this is just equal to -1. And that also makes sense, again, if we try to draw it, negative, the pi is all the way around, and our modulus is 1, so it's right over here, which is -1. And that's how we get -1 to the 1/4. And then if you try to do add your plus 2k pi, you'll see that it makes sense, because if we kind of reverse engineer this, then if we're taking 1e to the pi to the 1/4, then to find all our roots, we're going to need to add 2k pi to this. So it would be e pi plus 2k pi to the power of 1/4. And I just removed the 1 because it's unnecessary there. And so then we would get e to the pi over 4 plus k, 2k pi over 4. And I'm just doing that so it's easier to add them out later. And then again, we would have 4 roots, so we would go k equals 0, 1, 2, 3. And so when it's 0, it's pi over 4, which makes sense. And then when it's 1, you add 2 to it, so you get 3 pi over 4. Then you add another 2 pi over 4, which would be 5 pi over 4 and 7 pi over 4. So everything adds up, everything makes sense. Great. Let's move on. So clear all drawings, do the mouse, and move on. Perfect. And yeah, there we just plotted it, but it's not, we don't need to do that. Okay, simplify the following complex expression. So I don't want to copy that down to the other app I'm using, so that's why I'm just going to do it up over here. So what we're going to do is we're just going to multiply everything out. So at the top, we're going to get -1 minus 2j minus 2j plus 2j minus 4. And the way I got -4 is because 2j, and j and I are the same thing, just for everybody who might be confused. 2j times 2j is going to equal to j squared is -1, so it's negative, and then 2 times 2 is 4, so it's -4. That's how I got over here. And then that's going to be divided by 2 times -2 is -4, and then it's going to be plus 4j plus 4j. And all of this, let's not forget, is absolute value. Then if we continue, we need to simplify some stuff. Oh, that's not fun. That wasn't a good plan by me to put it right at the bottom. I could have put it up there, but I decided not to. So now you guys are going to have to look at my great arrow going right over here. So now if we simplify some stuff, the -2j and the +2j cancel out. So on top we get -5. So it's negative 5 over negative 4 plus 4j. We're going to take the absolute value of this. So then we can just factor out the negative. So then it would become positive. So it would be negative 5 over 4 minus 4j, absolute value of that. So the negative disappears because of the absolute value. And then I'm just going to split up this fraction. So it's going to be 5 over 4 minus 5 over 4j. And there you go. We simplified it and we left it in the form that we require, which is a plus jb. Yay. Okay, let's move on. And let's see if... Oh, I might have done something wrong. And the reason for saying that is because they got something else. Yeah. Yeah. Oh, okay. So the reason that Scott got a different answer is she actually simplified it a bit more than me. I didn't think of doing that. And what she did, let's see if I can pull back up what I had. Oh, doing something wrong. So if I just scroll up, there you go. So over here, if you noticed when I was scrolling past, we got to the same step, 5 over negative 4 plus 4j. But now what we're going to do instead is we're going to take the conjugate just to simplify it. Okay, so I'm just going to erase here. So we're going to get, we had negative 5, 5, negative 5. We can keep it like this. And the reason is because we will take the absolute value. So now we just have 5 over 4 minus 4j. And when we take the conjugate, it's going to be 4 plus 4j over 4 plus 4j. And that is going to be equal to 20 plus 20j over 16 minus 16. So these two cancel out. And the reason it's 16 minus 16 is just a squared minus b squared. And then we're left with 20 plus 20j. There you go. And that should be it. Over 32. Again, I made a mistake. Isn't it good that I'm kind of checking myself with her answers? So the mistake I made, and hopefully a lot of you at home caught it, and were screaming in the camera at me, saying, Reuven, what are you doing? And so what we're going to do then is we are going to, it's not 16, because it's 16 minus 16, and the minus comes from the j squared. So then it's going to be 20 plus 20j over 32. And you can continue simplifying. I feel like if I continue, I'll make more mistakes, and then I'll slow down the video. But hopefully that makes sense, guys. Okay, I'll clear our drawings, and now I can continue graciously. Hopefully I didn't confuse you with all my mistakes. Okay, so now let's do this, and this one I'm not going to do here. I'm going to go back to my other app, so it's 1 plus j root 2 over to the power of 8. So 1 plus j root 2 to the power of 8, and this is going to equal to, so what we want to do is we first want to take this into its exponential form, and the way we're going to do that is we need the modulus and the angle. So the way we get the modulus is we do, we're going to do is we're going to take square root of a squared plus b squared, right? So it's going to be equal to root of 1 squared plus root 2 squared. And that's just going to be equal to root of 5. And then our angle is going to be root 2 over 1. So that means it's going to be a tan of root 2 over 1. I don't believe that's a special angle, but I am going to check down over here if it is. But I don't remember any tan with root 2's in it. So tan pi over 4, we got pi over 3 is root 3. So we don't have any root 2's. So we can't simplify that over there. Perfect. So we just get a tan root 2. So then what happens is this, our exponential form would be modulus, and then e times I a tan root 2. So then we can bring it back up, and then we would take all of this to the power of 8, and we get root 5 to the power of 8, e I a tan root 2 times 8, and then you just have to convert it back to your rectangular form, and that's just again using the modulus times cos theta plus I sine theta. Cool. Let's move on to the next question. And so over here, we just see that that's what she did. And but then in the end, she just converted it back. And again, as you see, it's just as simple as cos of the angle, then the modulus, it's right over here. Perfect. Okay, so then we have ln of j. Ln of j, you're going to see that it's actually really, really simple. So ln of j. So we're just going to express j as our exponential in our exponential form. So the modulus over here is 1. And then the angle is just going to be 0 over 1. So it's pi over 2. That's our angle, because we're going to take a tan of 0 over. It's going to be 1 over 0, which is infinity, which is pi over 2. Sorry, I kind of messed that up here. Let me show you. If that confused anybody, so what I'm doing is again, so there's a 1 over here, and we have you can imagine your real part as 0. And so then we would take a tan of our real part over our imaginary part over our real part, so it would be 1 over 0, and inverse of tan of infinity, which is 1 over 0, is equal to pi over 2. So then we would get ln of e pi over 2, and then the ln and e kind of cancel out, you can think of it. So you're left with pi over 2. If you have more questions, if you need more explanation, message me on Discord or something, and then I can continue with that. Perfect. That's the mistake I made here. I just saw her answer. And so it's, when you do it, it's I pi over 2. I pi over 2. Or in her case, she uses j pi over 2. I just forgot it because it's e to the I theta. There you go. Okay, simplify the following expression. Your solution would be in the form a plus jb. So let's do this. So hopefully everybody's getting bored of transferring all our rectangular forms into exponential. If you're bored, that means you probably know it. So it's 5i or j to the power of 2j, 2i. I want to use I. Okay, so first again, we're going to transfer our rectangular form into exponential. So we're going to get our modulus is going to equal to root of 1 plus 25, which is 5 squared, so equals to root of 26. So that's our modulus. And then our angle is going to be, our theta is going to be a tan, to be more exact, a tan of 5, because it's 5 over 1. And so then our exponential form is going to be e to the I a tan to the 5 root 26. So all of this we're going to take to the 2i. So now if we just expand this, we're going to get root 26 to the power of 2i, and e I a tan 5 times 2i. So now what we're going to do is we're just going to express root 26 to the power of 2i using e. And just to, if anybody's confused, I just realized e is just a constant. It's called Euler's number. So if e as a thing is really confusing, you can just think of it as 2, but it's not 2. But again, it's just a constant. It's a number. Okay, now let's make root 26 to the power of 2i using e. So if you remember in class, what we did is we took root 26 2i. What we're going to say is that this equals to some x. Then what we're gonna do is we're gonna ln both sides. So we're gonna take ln root 26 to the power of 2i equals to ln of x. And the reason we ln is because ln has a very great property that ln a to the power of b is equal to b ln a. And that's what we're going to use here to bring down the 2i. So we're going to get 2i ln root 26 equals to ln of x. Finally, just to remove this ln from the right side, because we want to end up back here, basically only with an x, we're going to take both sides e to the power of that. So we're going to get e to the power of 2i ln of root 26 equals to x. And so that's how we're going to bring it up basically into e. Cool. So I'm just going to rewrite all of this over here. So we're going to get e to the 2i ln 26 root 26. And then this part over here, what's just going to happen is if I multiply I by I, it's going to be -1. I squared is -1. And so that's why we're going to have times e -2 times a tan inverse of tan of 5. Great. So now this is going to be our new theta because we have I over here, and this is going to be our modulus. So when we put it back into rectangular form, all that's going to happen is, again, our modulus is now e to the -2 a tan. That is a horrible tan. So tan 5 times cosine of our angle. So that's 2 ln 6, 2 ln root 26 plus I sine 2 ln root 26. And the only thing you would really need to finish this off is put the modulus in the brackets. Cool. That's how you do this part. Hopefully there aren't any questions. And that's it. Great. We finished the quiz. Now, before we go, I want to show you 2 more things just to be extra sure that we're all prepared. The first one is I'm quickly going to do demoivre. I don't know. I like to say demoivre. I think that's wrong. You can all make fun of me. Or not. I don't know. Demoivre. It sounds funny. Demoivre. I'll just stick with I don't know the pronunciation. Great. We're back here. So here it is. So we need to prove that z to the n plus 1 over z to the n is equal to 2 cos 2 theta. This one comes from the 2013 quiz, I believe. What we're going to do here is z to the n, and that's just this z to the n is just an imaginary number. So we can express imaginary numbers in many different ways, right? And so the way we're going to use here is we're going to express it as z to the n is equal to cos theta plus sine theta to the n. And now what I'm going to do is I'm going to go plus, and now here, this you can also think of it as z to the power of -n, because that's where the 1 would come. So then we would think of cos theta plus sine theta to the power of -n. Okay? Now what's going to happen is, if you remember, we have 2 forms. So cos theta plus sine theta is equal to, to the power of n. Important not to forget this, obviously. The power of n is equal to cos n theta plus sine n theta. And so that's what we're going to use here. Because we know these two are equal, I think that's De Moivre's theorem. I don't know, De Moivre theorem. So that's what we're going to do. We're just going to bring the n inside. So cos n theta plus sine n theta, that's a theta, plus cosine -n theta plus sine -n theta. Cool. So now what's going to happen is you really need to remember that sine is an odd function and cosine is an even function. Now, the reason that helps you is because if you remember even functions, f of -x is equal to f of x. And then sine is of odd functions, so odd. And what that means is that f of -x is equal to f of x. And what that means for us is that we can just rewrite this as cosine n theta plus sine n theta plus cosine n theta. And the reason I can do n theta is because negative n theta, and these are just the same functions right over here. It's an even function. So negative n theta just becomes cosine n theta. And this negative over here, we can bring it outside. So negative sine n theta. So then these two cancel out, and we're left with 2 cos 2 theta. Oh, and the way 2 theta came in there is in the original 2013, it just said replace n with 2. And so right in the end there, we see we get 2 cos n theta. And if we finally replace our n with 2, we get 2 cos 2 theta. And now quickly, if anybody's confused, what I want to quickly do is I'm just going to go to Desmos and just show you how, well, like that cos of x is equal to cos of negative x. See, it makes it a even function. They're equal. And the same thing with sine x, so that's my sine x, and then negative sine x. Oh, that's funny. Something's wrong here. Oh, because it's sine negative x is equal to negative sine x. And there you go, they're also equal. And that's that. Oh, and one more thing I quickly wanted to remind everybody about. So there's de Moivre, is just a distance in polar forms. There wasn't anything on the quiz. I was just looking through the PowerPoints to see what I would need to cover quickly. And I think most of the things we covered polar to Cartesian and Cartesian to polar. If you remember, we did that right in the beginning. Then we did distances L1, L2, L3. And then we covered how to go from rectangular to exponential to polar and from polar to exponential to rectangular. Actually might have not covered rectangular in imaginary numbers rectangular to like polar form, but that's you do it exactly the way you do it for polar. So if we have like a plus ib, if you want to convert that to polar, what you just do is you take the modulus, which is equal to a squared plus b squared, and then you find the angle by a tan b over a, and then we took the powers, we took the roots, everything's cool. The only thing I quickly wanted to mention is distances. If we need to do distances in polar form, what you do, so if you have like, let me draw a Cartesian plane. Yay, green's back. So if we have a point over here and a point over here, right, and we have our 2 lines, let me make those black. So over here are 2 polar. So what do we know? We know r, and we know theta. And we know this theta, so this is R1, this is R2, and then we have a bigger theta, okay? Now, the way you calculate distance then is like this. So you can imagine a triangle where we build our third line right over here, and then what happens is that you can calculate this inside angle. Let's change to red quickly. You can calculate this inside angle by doing theta 2 minus theta 1. And then what we get in the end is we get a triangle. So we have R2, R1, and theta. And we can calculate this distance using cosine law. And cosine law, if we name this A, cosine law A is equal to square root of R squared, R1 squared plus R2 squared minus 2 R1, R2 cos of theta. And that's the one thing I wanted to remind you. This is how you calculate distance in polar form. And that's it. Hopefully it helped. If you have any questions, again, text. Yeah. And you can always ask me if you're in a rush tomorrow, if there's anything more you need. Hopefully that helped.